have this weird thing.
All right, we're back. Yeah.
Okay, yeah. So I just wanted to show it based on the notes to shortcut it a little bit. So the fastest way that I know how to prove it is by introducing psi plus minus, which in essence is really just the expression that that you guys wrote. So essentially, it's really just saying what you wrote. You could have also just said we define phi a being equal to 1/2 delta a b plus I j a b psi a applied to psi. And then we are looking at the expression phi a phi b and prove that this is 0. And for that, we decompose it into the real part and the imaginary part and express those completely in G and J. And then we use the fact that if J squares to the minus identity, that we immediately get a number of relations out of it that I mentioned, of which we already proved a few, and you can try yourself if you can prove the remaining ones. And once all these relations are proven, you plug them into these equations, which are the real and imaginary part of this side. And that therefore implies indeed that phi inner product with phi is 0 for arbitrary a and b. And that, of course, then implies that phi itself is 0. So from that, it follows that phi a is 0. And that's exactly what we wanted to prove. Now, in the notes, there is also a way to prove it back, but there's some subtlety that I still need to resolve. But for the purpose of defining Gaussian states and understanding them, this is already very useful and sufficient. So let me now go back to the whiteboard. And
can you comment on phi A and phi B if there's anything like it just says that you take the state independently twice, or
yeah, there's nothing really subtle about it, no? So essentially, we want to prove that J squared implies that that 1/2 psi AB delta AB plus I j a b contracted with psi a psi b psi is equal to 0. No? And this object we just call phi a, in the sense that we can contract it that I mean such that for example we can define phi w being equal to w a contracted with phi a, for example.
Okay.
We could introduce something like that. And of course, if we, and as I said, our argument was supposed to be that phi a phi b is equal to 0. And if we can prove that, which of course as a tensor means it's true for any AB, if you express it in a basis, or more abstractly as a tensor, that this is 0 regardless of with what dual vectors W we contract it, that clearly implies that phi A itself is 0. So it's essentially a vector in Hilbert space and a vector in the classical phase space, so we can contract dual vectors, and we get 0. So in the end, it's really just a 0 map that eats dual vectors and maps it to the 0 vector in Hilbert space.
Okay. So I think now you clarified it. It's just, you know, because you have this abstract index notation, I think it was helpful when you said that actually this cat phi A is a 0 vector in phase space. Then, yeah.
Well, that's what we solved, no? Otherwise, we would say it's just a map. I mean, essentially, we can think of phi A as being a map that eats dual vectors, so from the dual phase space, and maps into a Hilbert space. And in what way does it do that? Well, it eats a dual vector WA and maps it to WA phi A.
But this is 0 in Hilbert space, yeah?
Well, that's what we prove, no? But before we prove it,
like for any choice of WA, it would produce 0 in the Hilbert space.
Yeah,
that is correct. That's what it turns out. But a priori, it's really just the object that we get if we contract WA with delta AB plus I JAB psi B applied to psi. Well, that's the exact definition. And from the property that if psi satisfies the condition that the associated J squares to minus identity, then this vector will be 0 for any W. Like, yeah. For a psi that does not satisfy that, no, like the logic was really, if you go back to the slides that unfortunately I don't have in here anymore, but if you go back, we started with a state psi. The psi defined the 2 point. So maybe I should give kind of this flow diagram. Psi defined ZA equal to 0. That was kind of the requirement, and C2AB, which we decomposed in GAB plus I omega AB. Now this GB gave rise to a J being equal to omega G, and this gave rise to this J gave rise to our delta AB plus I JAB with a 1/2, which is really just convention psi B applied to psi. Oh, and that essentially was our phi A. I mean, we could call it this way. And then we showed if and only if, or let's just put it like that, if J squared is equal to minus identity, this is equivalent to phi A being equal to 0. Does that all make sense now? So it's really a property of psi. It's essentially if psi squares to minus identity, if psi gives rise to a J that squares to minus identity, then the associated phi A is equal to 0.
Yeah. And in this case, phi A is an object that takes those dual vectors and can give...
No, not in this case. This is true independently if it's 0 or not. No? Like this equation here, this equation defines phi A as being a map that eats dual vectors if you contract with the A, and you get out a vector in Hilbert space.
Yes.
But not necessarily the 0 vector.
Yeah. And then if it's a Gaussian state,
if psi is a Gaussian state, then
this
J
map,
squared is equal to minus identity, and that implies that this phi A is equal to 0. Yes.
All right.
Okay, so at this stage, it was all very abstract, but let's actually prove a very interesting and nice property of this psi. Namely, let us prove that psi being so if we consider a Gaussian psi, so that means, remember, EA such that J squared is equal to minus identity, that this implies that psi satisfies Wick's theorem. And I found that really amazing, that essentially you can prove all these properties completely abstractly. So what does it mean that it satisfies Wick's theorem? Well, it means that psi A1 up to psi AN, which we remember we called Cn A1 up to AN, that this is equal to C2 A1 A2 up to C2 A N minus 1 AN plus, and so on, all other contractions, any two contractions. So we have a completely phase-space invariant covariant way to express the correlation functions, and I should say this is for n even, n is even, and 0 else. So the endpoint correlation function for odd n is 0. And I would say I use the remaining, well, we are actually already kind of, well, a little bit more than an hour, but I would say I should be able to prove within the next 5 to 10 minutes that this is satisfied. Any questions on that? Is it clear what it means? So just as an example here, C4 would be A, B, C, D, and their Wick's theorem would imply that we have C2 AB, C2 CD plus C2 AC, C2 BD plus C2 AD, C, B, C2. Yeah, so we express an arbitrary endpoint correlation function just in terms of the two-point correlation function. That's the magic of Wick's theorem, and is of course extremely useful when we're interested in calculation expectation values of observables with respect to a Gaussian state. And the C2, we remember, is fully determined in terms of G and omega. So it's quite nice. And there's yet one other subtlety, and that is that there are, so this is the bosonic version, and in the fermionic version we get certain signs depending on how we permutate. So let's say this is the boson version, and here I should also say boson. But for fermions, the only change is that we get minus signs depending on if the permutation of the indices A is even or odd. And it's all in the notes, so I should just remind you. I just posted in the chat again that we have this overleaf document that you can even edit and comment in if you have any questions. So this is the link where you have editing rights. Yeah, where we have the proof. Okay, so let me prove that, and for that, was there a comment by somebody?
No, I think so.
Okay. Okay, so we introduce the following object. So we introduce the object psi a plus, and this we define as 1/2 delta AB plus I J AB applied to psi B. So it's exactly the one that appeared before. And of course, sorry, this object we actually don't call psi plus, but psi minus. Okay. This is clearly not Hermitian, no, because we have an I in there and delta and J up real objects. So we can quickly check that psi a minus dagger that this is equal to 1/2 delta AB minus I J AB psi B. And we define this to be psi plus A. No, that's just a naming convention. And with that, of course, it immediately follows that psi A we can write as psi A plus psi minus. No? And of course, from the things that we had defined, we also have that psi minus A applied to psi. What do we get? It's a Gaussian state.
You get a 0.
Exactly. So what these psi's plus and minus are, they are a covariant basis independent way to describe creation and annihilation operators. That's the idea. So I will prove here the bosonic case. As I said, and for the bosonic case, it is very useful to check the commutation relations. So yeah, maybe that's okay. I think due to time, let's not do another exercise. I will just tell you that psi A, psi B with a plus, they commute. We get 0. And you can check it yourself by just plugging in the expression. And we also get that psi A, psi B with minus commutes. But if we put in psi minus A, psi plus B, we get exactly C2AB. And that's probably worth to quickly prove. So for that, I think it would be nice to have a volunteer. So let's just remember psi A plus minus is equal to 1/2 delta AB minus plus JAB psi B. And please prove that psi A minus psi plus is equal to C2AB.
This is valid for bosons and fermions now, yeah?
No, this is only valid for bosons. So let's put that in here.
Okay, so so the psi's have the omega. I mean,
exactly
okay.
exactly. So I can just as a remark, and you can check the notes for further details. We have the anti-commutation relations of psi minus A, psi plus B being equal to C2AB for fermions.
Okay, very interesting.
So there's an equivalent way for fermions. And of course, it's not very surprising because it's exactly what we expect of creation and annihilation operators.
So So basically, you made the size actually state dependent with the J,
Yes, exactly. They are
and
state
that's
dependent.
why something state dependent pops up in the commutation relations.
Exactly.
All right.
Exactly in the way this is also true for creation and annihilation operators. Just there you don't see it because you always express them in the basis that is fine-tuned to your state.
And it's like that for the vacuum state, yeah?
Exactly, exactly.
Okay,
You
so
can say
the
this.
regular canonical anti or commutation relations are done. And that's why people talk about all this normal ordering and so on, because they have a reference state.
Exactly, absolutely. All of this is essentially a basis dependent concept, and this is the way to describe it basis independently.
Okay, so Varun already started. So JAJB.
I guess I don't want to use B here since so I'll call it C.
Should you put the psi? I don't know. On the yeah, because
I mean,
yeah.
in here you don't need any psi actually.
Okay.
No. So here you really just use the fact that you can take out the delta in J out of the commutator. Because that was something we discussed at length with Marek. I don't know if he was happy with that in the end. But if something is not an operator, if it doesn't have a head, if it's contracted in a tensor, you can just drag it out.
I see.
Yeah.
So yeah, I was.
So you can just have here your commutator, and then you have here your delta A. Sorry, BD plus J. I mean, there's an I here, and I guess we can take the 2 1/2s out, and we get a quarter outside.
Good.
And then we have here I times BD psi D. Okay, and now maybe somebody else can continue, but my point is you can take the tensors out, so that you are left only with a commutator of the size.
So Varun, go ahead.
Right.
Yeah. So Lucas, you want to have just the regular commutator, right?
Exactly, because that's the only part in the expression, in the two expressions where we have a head.
Right.
Yeah. So delta BD plus IJ BD and one more, yeah?
Yeah.
Delta AC we have, very nice, minus IJ AC.
Yes.
Yeah.
And remind me again of the notation. So commutator for bosons, we said
It's
CD.
I omega. Exactly.
I omega. Okay. So 1/4. I am just repeating this. JAC delta BD plus IJ BD. Okay. And so we have I identity minus I omega G, yeah? 1 plus I omega G.
Yeah.
And then omega, yeah?
So if you do it as matrices, then you would need to do a transpose, actually.
Where do I need a transpose?
Well, in order to the
Yeah.
orders, if you want to move this inside, then you would need to do a transpose in the second expression. If you want to describe it as matrices, yeah. If you write it like this, then you should write it here as I mean, you are totally allowed to do that, but then you would write here an omega in the middle, no, as matrices, and then we need to look what's contracted with the D, and then we would get here an identity, which technically is a transpose plus IJ transpose.
True, yeah, because like
and that would be then
the C is here, yeah.
And that would be then exactly AB.
AB, yeah, okay. Good. So now we multiply out the whole thing, or?
Yes. Yeah, that's perfectly valid to do it this way. Yes.
Okay.
And of course, J transpose we can write as I mean,
yeah,
we remember that was G omega transpose, and of course that we can then rewrite well, G transpose. I mean, we can write this as G transpose omega transpose. And then we know that G is symmetric, so it's the normal one, and omega is antisymmetric, so we get a minus.
Well, I think I will thank you in 2 seconds. Okay, so I/4. The first one, identity omega identity, then identity omega ij. So we have with a plus I omega j t. So we had identity omega identity, identity omega. So now minus omega g omega and then identity, and then plus omega j omega j omega, but I need a minus here. Yeah. A B, is that correct? Yeah. So okay, so I guess we want to
well, here we see immediately that this is sorry, not there. Here we see immediately that that's J squared, so that's just
J
minus
squared,
identity.
minus identity, exactly. So I/4 have omega, and then we have minus
plus another, yeah, okay.
I just write it out, omega g omega, and then minus omega g omega, and then minus minus plus omega, yeah?
Yes, exactly.
And then AB. Okay, let's put like a white box. All right, so I/4. And then we have omega. I can write actually AB.
Yes. With the 2 in front, no? We have here the 2 omegas.
2 omegas, yeah, thank you. I didn't see that one. And then minus omega g omega. And what do we have for that one?
Well, it's probably useful to show that omega g omega is equal to capital G. So maybe somebody comes up with a proof for that. And of course there would be a 2 here, no? But how can we see that?
Yeah, so I could multiply a G. I get an identity, but this is minus J squared.
Yes.
One way or another, something like this, yeah?
Yeah. So
yeah, and you do it from the other side as well, I guess.
Maybe I would multiply it from the other side, yes?
No, I mean both, I think. Like, so you do it from one side first, Then you do it from
So you actually corrected so that there must be a minus, huh? That it's correct. Huh.
So we get a minus.
Yeah. Exactly. You're completely right with that. Yeah.
I half, and then we get omega AB, and then we get a plus I G AB. And are we missing one global minus?
Yes. So one minus sign is wrong somewhere.
A global one, or?
A global one? No. The I times omega is correct.
Yeah.
So where did something go wrong?
I put a minus, you can make a plus.
So how did here that turn into a minus?
But both of them were with a minus. That's
here's a plus and here's a minus. Where does that come from?
From this GT. So JT was minus G omega. So the transposition of J I had here.
I see. Okay. Oh, but here's a minus sign. So this should also be a minus sign, no?
I didn't see where, but I'm very happy you found it.
Here.
There's a minus sign, yeah.
And why is here a plus sign?
Yeah, fine. So this.
Or did you take out? No. That's right. No, like there should be a.
There's a plus sign, and then it becomes minus G omega, and then.
Yeah. So I would say this is a minus, this is a plus, and let's see for the other term.
Yeah, but then we need a minus sign here, otherwise they drop to 0.
Yeah, that's good. So let's figure that out.
So where is this one coming from? That was the term omega J omega and identity, and that one has to have a minus sign. Or?
Sorry. Oh, I see. Yeah, this one has a minus sign, I know. Oh, okay. No, I see. Actually, your signs seem to be correct.
So maybe one of those identities doesn't have a minus sign, yeah? For example, transposition of J is plus G omega.
That could be.
Then maybe it would work, or?
No,
but this one we need, but maybe the minus sign for this one somewhere.
Yeah.
Because what I got now is 1/2 of minus GAB plus I omega AB. Is that correct? Or is this still somehow an I in the wrong place? How was it?
Well, yeah, it should be here plus.
So C was G plus I omega, correct?
Yeah. 1/2 G plus I omega.
Okay.
So,
but the minus sign is somewhere here. I mean, this is just like collective blindness, but that's a computation.
I know where yeah. And that is, this one is the plus and that's the minus, because I claimed that we have psi A minus.
It's plus.
And the minus one has the plus, and the psi plus B has a minus. So okay, essentially, we calculated the commutator. We essentially calculated minus C. So that means we need to.
No, it's not even minus C, is it? It's a different object then, yeah?
But okay, it was minus C BC. So that means, yeah. So that means we need to take a minus sign of it. Then the G is correct, but with the wrong order of AB, but that doesn't matter because it's symmetric. and we now would be minus I omega, but BA. And then if we bring it in the order AB, from the fact that omega is antisymmetric, we end up with C2AB.
Okay, this is recorded. So
Yeah.
that can be a good exercise to rewrite.
Yeah, okay, so this was a little bit longer, but the
No, this is
conclusion,
fine, yeah.
the conclusion
Okay,
is
thanks for
psi
that.
minus A psi plus B is equal to C2AB.
And all right, so and then you were saying we were computing somehow the leg swap with a minus somewhere, but that's a different matter. We have this one and now the Wick's theorem, yeah?
Yes, exactly.
All right.
Yeah, I mean, essentially what I'm saying is we calculated this one, A psi minus B. We showed that this is equal to 1/2 minus GAB plus I omega AB. And now I'm saying if we bring this into the other form, this is equivalent to psi minus B, psi plus A being equal to minus this expression. So minus GAB plus I omega AB. So we end up with equal 1/2 GAB minus I omega AB. And if we now want to compare it to above expression, there we have AB, while here we have BA. That means we now need to switch A and B. So this implies that this is 1/2 GBA plus I omega BA. And if we now call A B and BA, we get exactly this equation. So it was all correct what we did.
So the minus was coming from the antisymmetry of omega, yeah? That was part of the okay.
If you want to correct it, no?
Okay.
No, you follow. And
yeah, I'm
see.
super happy with this. Thanks for adding the side note. Okay.
Okay, great. So now Wick's theorem. So what's the statement? I will be brief. I now took a bit longer. So essentially, I will just show you the case of the 4-point correlation function, and then you can look into the notes or do it yourself to figure out the general case. So here we have the 4-point correlation function, C2 A, B, C, D. So that's, of course, C4. And it should be quite quick to see that odd ones vanish, but because we will have an odd number of psi plus and psi minus. But let me just calculate that. So the trick is that we remember psi A is equal to psi plus A plus psi minus A. So that means we can write this as psi plus psi minus A, psi plus psi minus B, psi plus psi minus C, psi plus psi minus D psi. Okay. And then we also remember that psi minus A applied to psi is equal to 0. And hermiticity implies then, of course, that psi plus A is also 0. So that means immediately that we can remove here the psi plus, because applied to psi that's 0, and here the psi minus. So that means we are already simplified to psi minus A, psi plus psi minus B, psi plus psi minus C, psi plus psi with a D. And now we would like to commute stuff through. And for that, we remember what we just did, namely that psi minus A, psi plus B is equal to C2 AB. So, yeah, clearly in here, we can commute the psi minus and psi plus, and will be left here with C A B plus psi plus B psi minus A, but because the psi plus acts on the psi, that part will be 0, plus psi minus A, psi minus B. So that's kind of the first term. So we can put a parenthesis around this. And we can do the same thing in the second piece as well. Now we can put in the second piece that we have that we commute the psi minus with the psi plus, and we will end up there as well with a C2 CD plus psi C plus psi plus D psi. Okay, and now we can multiply that out, and we find immediately C2AB, C2CD plus, and now we get different combinations. So the other terms with the C's, like the C2 term with the plus term, will vanish because the plus will act on the psi and therefore vanish. And that means we are left with plus psi minus A, psi minus B, psi plus C, psi plus D psi. And here we apply again the commutations exactly in the same way as above. C2 AB, C2 CD. And when we do the contraction of that, we will get a C2 BC, and then the remaining two, as we commute them through, will give us an AD. And then there's the third and last term that appears after we have commuted them through, and we do another commutation, and that will be C AC2 CBD2, and that's Wick's theorem. And of course, we can apply that also to 6-point correlation function, 8-point correlation functions, and so on. And for any odd power of psi's, for example, if we only had here 3 psi's, then there would not be sufficiently ones to pair that we would commute through. That means in the end, we would always be left with at least one psi minus on the right or psi plus on the left that will annihilate the psi and therefore the endpoint correlation function for odd n will always be 0. So with that, I hope you believe me that we satisfy Wick's theorem, and we can generalize that also to fermions, in which case we get minus signs because we now not commute the xi's through each other, but anti-commute, and those will give us exactly the right minus signs in the fermionic Wick's theorem.
So then your construction would be, you had the commutator of psi plus minus, like we were computing, which is C. But for fermions, you just take anti-commutators of those psi plus minus.
Exactly. I said psi A minus psi plus B, that this is equal to
the 2-point function again, yeah?
C2AB. Exactly. Yes. Which you can prove in the same way.
All right.
Yeah, I mean, it was long, but
no, it wasn't. This was great. One question that I have in mind is that for and maybe that's a bit of a summary if you can comment on this. So you said like in a given basis we have the regular canonical commutation or anti-commutation relations. So for both fermions and bosons, you define this form, which is either coming from the commutator or the anti-commutator, and you have G or omega, right?
Yes.
But now for those covariant creation annihilation operators, in some way you fix it to something because you say this is the space, in some way that's a special basis, because previously the commutator was omega, anti-commutator was G, and now for those psi plus minus, those annihilators, in both cases you put it to C and the other one to 0, right?
Yes, but I'm not saying that I mean, it's a property of the xi's. The psi plus minus are state dependent, defined that they satisfy exactly these relations.
So yeah, so because you're proving it for a special state, they have some special algebraic relations. Yeah.
Yes.
And then whether you're fermions or bosons, you put the correct one.
Well, the beautiful property is that the xi's, they are independently, not like the definition of the xi's is independent of bosons, fermions, and then the correct relations just fall out. And I mean, I can give you a little bit of an intuition what the xi's are, namely psi JAB applied to psi B plus. What do we get? JAB.
In physics, that will be some eigenmode creation operator, right?
That's exactly right. But here we can even think about a math term. So we have here JBC psi C. And what do we get? Well, the J's squared to minus identity.
Yeah.
So that means we get here a Kronecker delta. I mean, essentially we get G AC plus I J plus I Kronecker delta AC psi C.
So now pull out the I.
Exactly.
And then you have the delta minus J no minus AC and then minus I. Okay.
So we get plus I psi plus A. So that means, and not surprisingly, the same is also true if you had put here a minus, if there were a minus. So essentially, we have that J, A, B, Xi plus minus B is exactly plus minus I, Xi, A. So you can
Nice.
think of these Xi's as so clearly J as it squares to minus identity is has eigenvalues plus and minus I, and it has plus and minus I with equal multiplicity, which follows from the fact that it's a real linear map. So that means on the complexified phase space, so if we allow for complex linear combinations, we can decompose this into the eigenspace plus I, direct sum V minus I. So this is 2n complex dimensions. This is n complex dimension, and this is also n complex dimensions. And so our Xi plus A is essentially spans the whole eigenspace of V plus, and Xi minus A spans the eigenspace minus I. So the way you should think about it is that if you start with observables, like let's just look at a single system with Q and P, then you remember that the standard way to create an annihilation operator would be 1 over square root 2 Q plus IP. No? But of course, even if you multiplied this with 6 or with 2i or an arbitrary complex number, it would still be an annihilation operator in the sense that it would annihilate the vacuum. And if you have several degrees of freedom, of course, any complex linear combinations of annihilation operators will still annihilate the vacuum state. So that means the space of linear combinations that will annihilate the state is an n-dimensional complex vector space. And that's exactly V minus I. So essentially, you can think of J telling you what linear combinations of Q's and P's as linear observables, as operators, Q and P, what are the correct complex linear combinations that lie in this n-dimensional complex subspace where each operator in that space will annihilate the state. And that's exactly the most information you can give about a vacuum state if you don't want to stick to a given basis. Because a given, if you don't have a fixed basis, there is no natural choice of creation annihilation operator number 1, annihilation operator number 2, and so on. The only information that you have is what is the space of annihilation operators. And that's exactly encoded in J as the eigenspace of J with eigenvalue minus I. Yeah, I would say with that, I'm finished. It was a bit longer, but I would say
super nice. Thank you.
Yeah,
I think that needs to be said. So bravo, Lucas. Super good stuff. Okay, so I stopped the recording. Thank you very much.
Sure.
Okay.